Welcome to section 5.1. So in this section we're going to talk about exponential growth and decay. We've already been talking about exponentials, but mostly we stuck to the form CE to the KT. And in this section we're going to start using, instead of C, we'll use P sub 0 or P naught. And that's the initial population, or just like the initial amount of whatever we're talking about. K is going to be called the growth constant, and T represents time. You'd have to read the problem to know if it's in years or minutes or whatever. And P of T is the population size. And then when we talk about population growth, the K is going to be something positive. If it's negative, that tells you it's decay. So we'll start with population growth though. So number 1, for the population of the city of Theed on the planet of Naboo, the equation is 467,409 e to the 0.201 t, where t is in years. What is the initial population? So we just talked about it, that this number that's out in front, the coefficient, that represents the initial size. So that would be 467,409. And that's people. What is the growth constant? K equals, and that's just the number in the exponent, 0.201, which is positive, so that does tell us it is a growth. Then it says find P prime of t and write it in terms of the original function. So my original function is P of t equals 467,409 e to the 0.201 t. So I have a constant times an exponential. So when I take the derivative, P prime of t, the constant I can just leave out in front and just focus on the other part. So to take a derivative of this exponent, it's really just the exponential e to the 0.201 t, but then I multiply by the derivative of the exponent. So P prime of t equals 467,409 e to the 0.201 t, and then times the derivative of 0.201 t, that's just going to be 0.201. So I think I did the first part. I found the derivative. Then the next thing I'm supposed to do is write it in terms of the original function. And this is pretty easy because this is the original function. So it's just P of t times 0.201. So far, I feel like this part is approachable. It's not too bad. Let's keep going with number 2. A bacterial culture grows at a rate that is proportional to its size. So this phrasing here, it's kind of like a key phrase. A bacterial culture grows at a rate. The word rate means derivative. So it grows at a rate that is proportional, meaning there's a constant, times its size, which is the population, P of t. So the phrase, something grows at a rate that is proportional to its size, means that it fulfills this relationship, which furthermore means that it's going to be in the this sort of format, CE to the KT. So I know that it's an exponential. It didn't say that, but I know that it is, based on that phrase. And it says at time t equals 0, there are 14 grams. So that gets me a little farther. That tells me that the C value is 14. And it also says that at 10 hours, there are 200 grams of bacteria. So at P of 10, so 14 e to the k times 10, right? I'm just plugging in 10. when I do all of that, I should get 200 out. So I have, this part's kind of confusing. It looks like there are two unknowns, but if you recall, the letter E represents a number, 2.718, something like that. So there's only one unknown, and that's K. So I can solve for K, and then I'll be able to write my equation. It says determine a function that models the size of this population as a function of time in hours. So that's what I need to do. I need to find K. So I think I want to get K by itself. The first thing I'll do is consolidate the constants. So that would be e to the 10k equals 200 divided by 14. And then to get rid of an exponential like this, I do a natural log on both sides. And then a natural log of e, that cancels and just leaves the exponent. Look, there's a 1 there perfectly for me to use. Let's see, yep. Okay, now I can divide by 10. K equals the natural log of 200 divided by 14 divided by 10. This is something I have to put into a calculator, which I'll do right now. Okay, natural log of 200 divided by 14 and then divided by 10. And I should check to see if there's a rule about rounding, because I'm going to have to round. Determine a function that models the size of this population. No, so it doesn't say when to round, so I'm just going to round to 2 decimals, which would be 0.27. So that's what K is approximately. So I'm going to do my equation as P of T is equal to C, which I learned was 14. It's in the problem statement. E to the K, which I found was 0.27 T. So one thing to think about is my K value is positive, which means it's growth, and that checks with what I was hoping I would get. So yeah, let me know if you have any questions. Let's go on to 3. Okay, a population of wombats is growing in an exponential manner and doubles in size every 12 years. Okay, determine the growth constant for this situation, rounded 2 decimals. So I think the way I would approach this is, I'm noticing that it doesn't tell me what the initial amount of wombats is. So I'll just stick with C. P of T equals C, e to the KT. But I know that 12 years later, it's going to double in size. So I know that, let's see, so the initial amount is C. So if it doubled, that would be 2C. So 2C is going to equal C e to the k times 12. Yeah, and actually that works out great because I have a C on either side, which means that it'll cancel. So now I'm just going to solve 2 e to the 12k. So let me read my problem statement because I just started doing something. I'm not sure this is the right thing. So it says determine the growth constant for this situation, rounded 2 decimals. Okay, I was on the right track. That is good. So I have 2 equals e to the 12k. I want to get rid of the e, so I'm going to take the natural log of both sides. Natural log of 2 equals the natural log of e to the 12k. And then natural log of e to a power simplifies to just be the power. So then I can reduce that by dividing by 12 on both sides. Natural log of 2 divided by 12. And I'm supposed to round to 2 decimals. So I'll put that into a calculator. Natural log of 2 divided by 12. Rounded to 2 decimals is 0.06. Okay, and so it just said to determine the growth constant. So I did that. I can't really put a whole equation together because I don't know how much there was originally. But actually it looks like part B helps me with that. So part B says if the initial size of the population was 2,000, how large will the population be in 10 years? So them telling me the initial size makes it so that I can write my equation. P of t equals 2,000 e to the 0.06 t. And then to solve this, it just wants to know what it was like 10 years later. So P of 10 equals 2,000 e to the 0.06 times 10. That is a calculator thing. E to the 0.06 times 10. That is roughly 3,644.23. So I would round down for this one because you wouldn't say you've got like 2/3 of a wombat. So just go with that. 3,644 wombats. Okay, part C. I think I might sneeze. No, I'm okay. How fast will the population be growing in 10 years? Okay, so I need to take a derivative here. So P prime of t is going to be, so I'm going to leave this constant alone, 2,000. And then to take the derivative of the rest, that's just e to the 0.06 t. And then I multiply by the derivative of 0.06 t. So P prime of t is equal to 2,000 e to the 0.06 t times, so derivative of 0.06 t is just 0.06. So I think this is like an interesting moment here because I'm about to do P prime of 10 because I want to know what's happening 10 years later. So I already know that this part right here, that's the same thing as P of 10. So let me write that. So 2,000 e to the 0.06 times 10, and then all of it times 0.06. So I just put this into a calculator, right? And that's what I got up here. So 2,000 e to the 0.06 t. When I did that, I got 3,644. So instead of putting this into my calculator again, I could just take this value and multiply it by 0.06. But either way, maybe that doesn't feel all that comfortable to you. I will put this into my calculator. Okay, when I do that, I get approximately 218.65. So, how fast will the population be growing in 10 years? 218 wombats per year. That's pretty cool. So I want to check my units just to be safe. Okay, so I'm just making sure that they always used years every time, and it looks like they kept using years. So, yep, that would be, excuse me, wombats a year. All right, part D. In how many years will the population reach 10,000 wombats? Okay, so to do that, I want to know when P of t equals 10,000. So that's 2,000 e to the 0.06 t. And I can cross out these zeros and then divide by 2, a little bit of mental math. I get 5 equals e to the 0.06 t. I'll take the natural log of both sides. So natural log and e are going to simplify to just be this exponent. And then I would divide by 0.06 and get that t equals the natural log of 5 divided by 0.06. And put that in a calculator. Okay, that would be 26.82. So one thing we have to think about here is that in how many years will the population reach 10,000 wombats? So in 26 years, like exactly at 26 years, it won't have reached 10,000 wombats. So like in words, it might be worth saying between 26 and 27 years. I would also accept saying 26.82, approximately 26.82 years later. Either would be fine by me. Okay, let's pause here.